Dear colleagues, let's start our today's talk. Our speaker is Zhang Butian, and he will tell us about combinatorial cocycles in the space of long nodes. Let's welcome.
Okay, thank you very much, and thank you for the invitation to the Moscow Beijing seminar. I'm honored here to give a talk, and my title is Combinatorial One Cycles in the Space of Long Nodes. In this talk, I shall briefly talk in four parts. The first part is introduce the space of long nodes. And the second part is about the finite type combinatorial one cycles in this space. For the part 3, if time permits, I shall briefly introduce the method for the calculation. And furthermore, we will talk about recent work, joint work with Thomas Fiedler about the quantum equations derived from a regular one cycle. So let's start. Uh, the space of long nodes. Let's recall the definition of long nodes. Compared to the traditional knot, which is the embedding of S1 in R3 or S3, the long knot is the smooth embedding of R1 into R3, such that it can only be knotted at the unit interval -1 to 1, and the other part of this embedding just coincide with the standard embedding of the x-axis in R3. Here I draw two examples in diagrams. One is a classical knot diagram, which is an embedded circle, and the other one is the long knot. As you can see, probably there is a 1-1 correspondence between these two kinds of knot, between long knot and knot. We will talk about it more in detail. For the two knots, for the knots, we usually consider it up to isotropy, and for the long knots, we do the same. Since we usually describe them by diagrams, so we say that two diagrams are equivalent even only if they are connected by a sequence of Reidemeister moves. And for long nodes, the Reidemeister moves are similar. There are three kinds of Reidemeister moves. Let's recall them. The first one is R1 move, which is related to adding or deleting a curve on the diagram. There are different types, four types in total. The second one concerns about the tangency of the diagram. And the third kind, Reidemeister move, is concerned with the triple point of the plane curve. Okay, these are the Reidemeister moves. From a Reidemeister move, we can construct knot invariant. Since knot invariant are very important in knot theory, it is an essential tool to study, to distinguish knots. And the first remark I want to talk about is the difference between knot and long knot. Up to isotropy, up to knot types and long knot types, actually there is a 1-1 correspondence between them. Because if you have a long knot, you can complete it by adding a point at the infinity point, and then it will give the embedding of the circle in the S3. So these map forms a 1-1 correspondence between the isotopic classes between of them. That is to say, you don't have to concern a lot. The long knot and knot, if we study them up to isotopy, there is not much difference. And the knot invariants we have known now, there are lots of knot invariants. Knot invariance is a map from the isotopic classes to some set, no matter to polynomial or values, numbers, or even set, etc. These are a brief recording of the knot theory. And now let's come to our objects, space of our objects, the space of long knots. And when we say space of long knots, it means a set formed by all the long knots equipped with the C infinity topology. I shall explain what is this C infinity topology briefly. For the C infinity topology, that is to say, for two elements in this set, K through 1, since each element is an embedding, a map, we can study their derivatives. So in this C infinity topology, two elements are close to each other, two embeddings, two long knots are close to each other if up to some fixed ordered derivatives are close to each other at each point. This is the C infinity topology. That is to say that we do not only ask at each point of R1 the image of the 2 points are close to each other, but also at this point the derivatives are close to each other. This is the C infinity topology. And it turns out that under this topology, the path components of this space K through 1 coincide with the isotopic class of long knots. So each component of this space corresponds to a long knot type up to isotopy. So it turns out that the zero cocycles of this space is exactly the knot invariance. So now there is a natural question is that what about if we go one step further, what about the one cocycles in this space? The zero cocycles are the not invariant, and one cocycles. What does it mean? What can we extract from the by the one cocycles? What information can we get using the one cocycles about each component, each knot types? That's the question now. And
Oh, I'm sorry.
yes,
I think I could understand the definition of Whitney symphony topology. Could you tell me again?
okay, no problem.
Mm.
So I shall not tell the real definition precisely, but I shall give you an intuition. What does the C infinity topology gives? That is to say, I shall describe two embeddings are close to each other. That means what? I shall describe this. In C infinity topology, two embeddings are close to each other if at each point their images are close to each other and their derivatives are also close to each other.
And for each x in R1, f0x and f1x close, and their derivative is also close for each x in R1, right?
Yes, for each x.
Oh,
yes,
thank you.
because
Thank you. I
here,
understand that.
yes, thank you. Maybe I should say that if you, because here we have asked that outside the unit interval, it is always the standard embedding of the x-axis. So here we say for all each point, there's no problem of compactness. Since for the C-infinity topology, there are two types, which is a strong type and a weak type, weak version. Here, the two versions coincide because our long knots is somehow compactly supported. Okay, that's just a remark. Now I shall talk about, before talking about the one cocycles, I shall talk about this one cycles in this space of long knots. One cycles, that is to say the loops, and more generally the arcs in this space. And the arcs and loops in this space can be described in different ways. If you write an explicit isotoping formula, actually this gives an arc in this space. And if you are describing using diagrams, an arc in this space is given by a sequence of Reidemeister moves. And if you watch a video, an arc in this space is actually given by a movie centered at a specific long knot. So perhaps I shall show you a video which represents an arc in the space of long knot. Let me change to the video. Okay, so now in this video, we will see a knot which is actually the long knot version of the 4-1, the figure 8 knot. And let's see what is an arc in the space of a long knot. Okay, that's all. As you can see, this knot has many isotopies during this video, and this represents an arc in the space of long knot. But since the first at the beginning and at the ending actually it comes back to itself, so it actually forms a loop in the space of long knot. Let's come back to the slides. A loop in this space is an arc which has the same beginning and ending. Having an intuition about the arc and loops in this space, I shall show you some specific examples, classical loops in this space. The first one is called the Graham loop or the Graham cycle. Since we have a long knot, we can always do a rotation along the axis, the x-axis of that long knot. If we turn it one round, it will come back to itself. the original position, and this forms a loop in the space of Laurent. This is called the Grumman cycle or the Grumman loop. And in diagrams, it has an interpretation by pushing the diagrams through a curve. Here in this slide, if we have a Laurent diagram K, we first add a curve at the end of this diagram, and then we push this K as a very small bead along this curve. And then we will come back, and then we delete this curve at the end. It will comes back to the original position. This is a diagrammatical realization of the rotation along the x-axis, which represents the Grumman cycle. The second loop is called the Fox-Hatcher loop. For the Fox-Hatcher loop, I shall only describe it in diagrams this time. If we are given a knot diagram, for example here, it is 4-1, the figure 8 knot. The Fox-Hatcher loop is realized by a sequence of Fox-Hatcher move. And what is a Fox-Hatcher move? Fox-Hatcher move is to put the last crossing of the knot diagram to the first crossing. For example, here, if we start from here, you can see that the last crossing I draw with the purple, with the small purple disc. That is the last crossing. And we can put it to the first crossing as here. From here to here, it is the Fox-Hatcher move. And we do this Fox-Hatcher move consequently. Since in this diagram, 4-1 has 4 crossings, so after 8 Fox-Hatcher move, it will comes back to the original diagram. This is the Fox-Hatcher loop. But accidentally here, because of the symmetry of the 4-1 of the figure 8 knot, we actually do only 4 Fox-Hatcher move instead of 8. The diagram has already come back to itself. Yeah. So it turns out that for some knot diagram, this Fox-Hatcher move can be split into smaller loops. Okay, that's a remark. And for more
Excuse me.
complex, yes.
I have a question. Here, why this loop is called Fox-Hatcher loop?
Sorry, why could what?
Yeah. Why this loop's name is Fox-Hatcher loop? Why is named by those two mathematicians?
Okay. Okay. So this name first, I should say that this loop was first introduced, or I should say this Fox-Hatcher move was first introduced by Fox in 1966 in his article about the knot, what he is called rolling. And rolling is exactly this move from here to here. This is what he called rolling. He introduced this to study the knot spinning way to construct the embedded surfaces in 4 spaces. That's
I see.
yes. And then about in 2000, I don't remember the exact year, about in 2000, Hatcher Hatcher has studied this operation in the context of the space of knots. So this is why this loop is called the Fox-Hatcher loop.
Oh, I see. Thank you. I saw same rolling move introduced by Zeeman to construct a sphere in four space. So yeah,
Yes.
maybe all of them
Yes.
are same have the same thing. I see.
You are right.
Thank
It originally comes from the construction of the embedded surface. Yes.
Yeah. Thank you.
Okay. And for the more complicated knots, actually we have more loops or the arcs. For example, here in if we have the connected sums of different knots, here I draw the figure 8 connected sum with the trefoil. For example, here, if we at the beginning we have the trefoil connected sum with figure 8, and then we can first imagine this trefoil to be a very, very small one, small bead, and then we can push it along this figure 8 knot. So we will get from the 3-1 connected sum with 4-1 to 4-1 connected sum with 3-1. And this is called the push arc. What is called the push arc in the space of long knot. And if you do this again, but this time if you do this again for the 4-1, for the figure 8 knot, you imagine it as a very small bead and push it along the trefoil, and it will come. We will come back, and this will form the loop. What we call it is a bracket loop. A bracket loop, that is two push arcs composed by two push arcs, and we call this one a bracket loop. And this loop exists for the connected sums. And sometimes if we consider the connected sum of two same knots, for example, if here we do not consider the connected sum of 3-1 and 4-1, and instead we will consider the connected sum of, for example, 4-1 and 4-1. In this case, if we only accomplish just one push arc, we will come back to the original position, and it will only form. It has already formed a loop in the space of long, and that loop we will call it the half bracket loop. But it is not exist in general. It just exists for the connected sum of a knot with itself. That is the half bracket loop. So these are all the examples, explicit examples in this talk I shall introduce about the loops or arcs in the space of long knots. And having talk about the one cycles, I shall talk about the one cocycles in the space of long knots. I shall first introduce some known one cocycles before. The first one is the Tuplin-Turchin's one cocycle, V3. V3 is a one cocycle of finite type of order 3 in the sense of Vasiliev. It is the first discovered by Tuplin and Turchin around 2006, something like that.
No, well, why do you say 2006 if it were published in Vasiliev's book in 20th century?
Okay, thank you very much for this explain. Yeah, maybe in 1990 something, 8 maybe. Yes, since Vasiliev have and Tuplin-Turchin found this perhaps later they published it. And later, maybe the published paper that I meant from Tuchin, he calculated this one cocycle over Z mod 2 using a combinatorial description. And the rot F here is a long knot, some long knot. And rot is the Graham cycle, means the rotation. And the value of this one cocycle V31 equals mod 2 equals to these values. And later the Sakai, Keiichi Sakai has constructed using another method called the graph configuration integral. He constructed a one cocycle, and this one cocycle is an R-valued one cocycle. It turns out that he and his colleagues also calculated the values of the I gamma, this one cocycle, on the loops that we described earlier. Maybe some notations I should explain here. FH0 is the Fox-Hatcher loop with respect to the zero framing, because there is some subtle things about the framing when you try to describe it. And for the bracket loop, F1, F2 bracket 0, here the 0 also concerns about the framing. It means that we will give both F1 and F2 zero framings when we are doing the push arc or the bracket, the whole bracket loop. And we also have Mortier's one cocycle alpha 1 3, which is a Z value, and he also calculated the values of his one cocycle. This one cocycle alpha 1 3, alpha 3 1 is a combinatorial one cocycle. We shall introduce it more in detail very soon. As you can see from these values, actually these three different one cocycles seems to describe the same in somehow. They are correspondents to each other. Their values are very, very similar, or even we could say that they are the same in these specific loops. Hence, we conjecture that especially for the alpha 131 and the V31, actually we conjectured that they actually describe the same one cocycle. And Thomas Fiedler, yes.
Oh, may I ask you? I would like to ask one thing. Here, you introduced three kinds of one cocycles, right?
Yeah.
But you just mentioned the values of three, the rotation Fox-Hatcher loop and bracket loop, three kinds of loops, right?
Yes.
Can we say they are all loops in the all loops for the space of long knots?
No, I cannot say that. I cannot say that.
Just we are interested in those three
Yes.
loops. Okay, thank you.
Yes, actually, that is also because we only calculated the values of these one cocycles on these specific loops. For alpha 1 3, now we have calculated actually more values on more loops. But for I gamma or the V31, oh yes, I should mention a result of Mortier. He has shown that alpha 31 mod 2 equals to V31 on all the loops. Yes, thank you. I forget, I should mention this. V31 mod 2 equals to alpha 31 mod 2 on all the loops. Was a work of Mortier. He has shown this. but we don't know whether over Z they are the same. This is something that we don't know yet. And for the one cocycles, the calculations on the loops was somehow difficult. It turns out that only these loops on these loops the values has been calculated. And more complicated loops, well, either people do not do it, either there are some difficulty in calculating it. And also, later we shall talk about in detail the combinatorial one cocycles, which was introduced by Fiedler, Thomas Fiedler, by viewing the diagrams and the random master moves. The combinatorial one cycle is a map from the generic path in the space of Lau to some abelian group G. Generic path, you can just imagine it. You can just imagine it as the sequence of randomized moves. That is what we mean by generic paths. Satisfying two conditions. The first one is that this map should be additive. Should be additive respect to the concatenation of the path. And the second condition is that it should have the same value on two path homotopic paths. If we have such a map, then it is a combinatorial one cocycle. And it turns out that if it's satisfying these conditions, these one cocycle represent real one cohomology classes in the space of Lau. From these two conditions, actually from the first one, it forces this map have the following form. That is the sigma of a sine of some master move times some weight function. So if we want to construct the combinatorial one cocycle, we need to have some combinatorial description of the second condition of this path homotopic condition. How do we describe two path homotopic paths combinatorially? If we know this, then we can, just as construct the knot invariants by randomized moves, we can construct one cocycles. To give a combinatorial description, we need to have some analog of randomized moves, which we shall call the higher randomized moves for the generic paths in this space. The classical randomized move corresponds to three kinds of singularities of codimension 1 of plane curves, which are shown here. And if we want to describe for the path homotopic path, we need to go one step further to study the codimension 2 singularities of the plane curves. There are 6 types of codimension 2 singularities. 5 types are shown here, and one more type is a combination of 2 disjoint one codimension 1 singularities. For example, 2 separate are triple points, for example. And around these 6 types singularities, there are some generic loops which are called meridians around these singularities. For example, here we have shown a meridian around 2 triple points. And here is a meridian around a tangent triple point. Here it is a meridian around the intersected cusp. meridians around cubic tangency and rhomboidal cusp, and the most complicated, the ordinary quadruple point. By studying these singularities, we will have a higher right-master moves for the path homotopic paths. That is, two paths are path homotopic if we can do some higher right-master moves, which is if a path lies on some part of a meridian we described earlier, we replace that part of the meridian by the remaining part, the other part of that meridian. This is what we mean by higher right-master moves. So around that 6 types of singularities, there are 6 types of higher right-master moves. The two generic paths are path homotopic in the space of long knots if and only if they can connect to each other by a sequence of these higher right-master moves. So having this combinatorial description, we can transform our second condition into the map phi for that combinatorial one cocycle is equals to 0 on all the meridians around that 6 types of singularities. This is what we call the cocyclicity condition for the construction of the combinatorial one cocycles. And now I shall show you the main result of this part is that we have constructed two new one cocycles of combinatorial order 4, and we have in the space of long knots, and we have calculated their values on the loops that we mentioned earlier over Z. These two one cocycles we call it by beta 1 and beta 2, and their values are on the loops that we described earlier as the following. Here, V2, V3, and V41, V42 are the Vasiliev invariants, or the finite type invariants, of order 2, 3, and 4, respectively. So it turns out that all our one the beta 1 and beta 2 given here have the values of finite types. And these are the one cocycles over Z. These two one cocycles are linearly independent, and they represent non-trivial one cohomology classes by these calculation results. We say that one cocycles are non-trivial, it means that it represents non-trivial one cohomology classes. And over Z mod 2, there is one more one cocycle, which we call it beta 3. Beta 1 and beta 2 survives mod 2 also, and beta 3, it turns out these three will form linearly independent set of the one cocycle over Z mod 2. I should remark that this beta 3 has value 0 on all the loops we described earlier, but it is still non-trivial. It is a non-trivial, it represents a non-trivial one cohomology class. And this is proved by calculated on the half Fox-Hartree loop. If you remember that the 4-1, because of the symmetry, it can be, the Fox-Hartree loop can be split into smaller loops, and we can calculate beta 3 on these smaller loops. And it turns out for some more complicated knot, this beta 3 is not have equals to 1 on that loop, so it is non-trivial. I shall talk about how do we construct these one cocycles. These one cocycles are constructed using Gauss diagram. That is to say that we have to give a weight function for the R3 moves. The weight function here is described by Gauss diagram formula or some extended Gauss diagram formula. For the long knot, if we are given a knot diagram here, we have a corresponding description by the Gauss diagram, which is an oriented circle represent the R1. Oriented is oriented as counterclockwise. And the infinity point is represented by this blue base point on the circle. For the arrows of the Gauss diagram, it represents the crossings of the diagram. Here we use the foot of the arrow to represent the undercrossing, and the head of the arrow to represent the overcrossing. And the sign of the arrow is exactly the sign of the crossing. So for example, if here we go through from the left to right of the long trivial diagram, we will come to the first crossing at the undercrossing. So here it is the corresponding move in the Gauss diagram is that if we go from the base point, blue base point, counterclockwise, we will meet the first arrow at the foot. That represents the first crossing at the undercrossing. This is how the Gauss diagram corresponds to the knot diagram. And for the R3 moves, the corresponding change in Gauss diagrams looks like this. R3 moves, this change is local, concerns about the 3 crossings. The 3 crossings in Gauss diagrams are the 3 arrows. In this Gauss diagram, it is in blue. The 3 arrows in blue, corresponding to the 3 arrows here in the diagram. If we are doing a right mass move, it will change from left to the right. And this change R3 move is local. So in Gauss diagram, it only changes the relative position of these 3 arrows. And at some point, you can see that it just concerns about triangle areas changing of the arrows. And this triangle here, we use it at the middle of the 2 Gauss diagram to represent this triangle moment. This triangle moment. This is how the R3 move behaves in Gauss diagrams. As the classical Gauss diagram formula, we will extend that spirit to the one cycles or the one cocycles. That is, we will define a bracket using Gauss diagram on some random mass move. For example, here P represents the R3 move described here. How does this bracket works? It means that we will count how many times this configuration, this Gauss diagram appears at this moment, at this R3 move moment. We will count how many times it appears as a subdiagram of this R3 move with a weight. And this weight is given by the product of the sign of the 2 arrows here and here, which are not the triangles, which does not form the triangle. For example, here, when we are doing our R3 move from left to right, at the moment we get a Gauss diagram like this. And for this configuration, we can see that it's actually appears exactly once in this R3 move as a subdiagram. It means only one subdiagram of this R3 move looks like this. And now we see that with these two red arrows. And the sign are minus and minus. So the weight of this appearance equals to -1 times -1. Since it only appears once, so it has only such one contribution. So this bracket equals to 1. And at the bottom row, I wrote these three Gauss diagrams. They have signs. Since if it is labeled, we can see that these Gauss diagrams do no longer appears as a subdiagram because the sign of the labeled arrow does not correspond. Either the sign of these arrows or either the triangle has different shapes. So it equals to 0 or it equals to 1 according to the definition. And our one cocycles, the weight functions is given by the linear extension using this bracket on the right master moves R3. Our one cocycles beta 1, beta 2, beta 3 are all in this form with this weight function W beta I is given by Gauss diagram formulas. For example, for beta 1, it is given by Gauss diagram formulas of these combinations. Of course, we have coefficient 1 or -1, just a linear extension using that bracket. And for this is for beta 1, and this is for beta 3 over Z mod Z, over Z mod 2. And so coefficient -1 equals to 1 for Z mod 2. I shall not display the beta 2, which has 49 terms in total. As you can see that here our configuration for the weight functions has at most 2 arrows, which is not in the triangle. And this forms the notation of the combinatorial order. The combinatorial order is the maximal arrows outside the triangle plus 2. And that is to say that we treat this triangle as a true, as 2 arrows. And we conjecture that this combinatorial order coincide with the finite type order, this defined by Vasiliev. Just as the classical Gauss diagram formula, which has which has a connection between between Gauss diagram formula and the description of finite type invariance in the sense of Vasiliev. Here we conjecture that for one cocycles, there are also such a connection, but it is not really proved here, but it is supported of our work and also the work of Victor Tushin by calculating the upper bound of the
By the way, are you in contact with Turchin? I communicated with him a lot, something like 20 years ago, but since that, I have absolutely no contact.
Okay. Okay, thank you for this information. Since Tuchin, he has calculated the upper bounds of for the one cocycles in the sense of Vasiliev. He calculated that for the order 3, there are exactly 1 over Z, or over Q, I should say. Over Z? Yes, over Z. He has calculated the for the and Vasiliev they have calculated for order 3, there are only a unique one cocycle, which is the V31. And for order 4, Turing has calculated the upper bound of order 4 over Z mod 2 is 2. So here we have found two one cocycles described by the Gauss diagram formula described here, which seems to have matches well with the upper bound of that of Turing's calculation. So that's why our results support this conjecture. And for the rest of time, we do not have time to explain the calculations. How do we calculate it? So I shall not skip this part and come to the part of quantum equations. And the quantum equations, that is, we shall no longer consider just the space of long knots, but the space of two string links. Here is an example of the two string links. Analog, so I shall not explain the definition of the two string links. And the one cocycles we will use is a regular one cocycle introduced by Thomas Fiedler. This one cocycle is valued in a Heck algebra H2VZ. This Heck algebra is described by has dimension 2, with the coefficient in this ring, in this Lohan polynomial ring, with the basis of this has dimension 2. It satisfies the scaling relation, that is to define the product of these corresponding to a regular version of HOMFLY-PT polynomial. And in this part, we will use this one cocycle, which has values in this Heck algebra. We consider the following loops in the space of two string links. That is to consider the connected sums of some 2-2 tangle with two cable parallel two cable of some knot diagram with the, of course, with the blackboard framings. And then we can push this small tangle along that diagram of 2D as the case of the connected sums of long knots. If D and D prime, if the D and D prime are regularly isotopic, that is to say, only use R2 and R3 moves to get from one to the other, then it will induce isotopy for the 2D to 2D prime. We call it gamma here. And then, of course, it also induces the whole isotopy from T connected sums from 2D to T connected sum to 2D prime. And the loops, or the two paths I showed you here, is actually a contracted loop. Since it is contracted, that is to say, our one cocycles on the values of this path equals to the values on this path. Contractible. That is to say, okay, this is an example of 6-1 or 6-2, or maybe probably 6-2 with a tangle like this. And our one cocycles on these two paths should be equal. So we put these two things on the left and the other two things on the right. For the things on the left, if we have given 2D and 2D prime and the T, these are something we can calculate. For the things on the right, since we don't know if we're given T and then D prime, we do not know actually how they are connected, usually. Otherwise, you give me this gamma. So this part is something that we usually don't know. But this part is something that we can always calculate it. And for this part, we call it delta t. And by some analyzing of these of the position of the t and 2D, we can find that this thing equals to this thing, has a form like this thing. What is this thing? Let me remind you that this delta t is has two coordinates because it lies in the Hack algebra of dimension 2. So we regard it as a vector, as a column vector with the two coordinates. And this AT and XT, AT is a 2-2 matrix which can be obtained by some analysis, and it depends only on T. And X gamma is a column vector of two coordinates. Two coordinates, we say it here and here. These are the two coordinates for X gamma, which depends on the regular isotopy gamma, but not on T. We obtain this by some analysis, a lot of analysis. For two specific tangles, T1, T2 here, our matrix AT actually looks like this. For example, for T1, we will obtain this. So our matrix AT equals to 1 Z 1 plus Z square. These are the matrix AT. And for T2, our matrix AT equals to like this. But it should be noticed that for T1, T2, the X ID and X sigma 1, the two coordinates of X, it turns out coincidentally, it turns out to be the same. So for this XID and X sigma, there are some informations about the isotopies connected, regular isotopies connected from D to D prime. These are something usually we do not know. But delta ID T1, delta ID sigma 1 T1, these are something we can calculate it using the one cocycle. These are something we can get. From this way, we will get some information about the regular isotopies connecting two knot diagrams. For example, for this one, if we suppose that sorry, I should mention this system of equations are called the quantum equations for the two stringings. These quantum equations can be used to distinguish knots. That is, how should we do that? If we have two knot diagrams, D and D prime, and we put it in the same, with the same Whitney values and the rise, and then if they are isotopic, then they are regularly isotopic. If we suppose that they are regularly isotopic, then we will have this contracted loop. Then we will have these quantum equations. And these quantum equations should have a solution in this ring. And for two diagrams, if by solving these equations, if the result is not in this ring, is not a Lohan polynomial, or the result of these two equations are not the same, that means our hypothesis D and D prime are regularly isotopic are false. That is to say, they are not isotopic. In this way, we can distinguish knots. For example, for 6-1, 6-2, these two knots in a good position, we can solve the quantum equations of these quantum equations 3. And it turns out one of the coordinates here equals to this guy. And as you can see, there is a factor in the fraction which cannot be factorized. So it means that this thing does not lie in the Rohan polynomial ring. So that is to say 6,1 and 6,2 are not regular isotopic and hence not isotopic. And this is how we distinguish knots by using these quantum equations. Yes.
Do you have any have you distinguished knot invertibility anywhere?
Yes, it turns out no. I shall talk about this more. Perhaps at first I shall talk about what we can do, and then I shall talk about what it cannot do. These are the results that we have calculated based on this one cocycle R1 regular. It can distinguish, usually it can distinguish different knots. And for the 942, I should remark that the HOMFLY-PT polynomial cannot directly distinguish it by just looking at the HOMFLY-PT polynomial. Its mirror image and itself have the same HOMFLY-PT polynomial, but they are not isotopic. But our one cocycle quantum equations here can be used to distinguish them. I should say the Alexander Conway version is just you put the A or V equals to 1 in the construction of the scaling relation. Okay, I shall not expand this part. A Conway knot and this Kinoshita-Terasaka knot are the mutants, and it turns out no, they cannot be distinguished using this method. As for the what Professor Monturov asked for the invertibility of the knot, for now our answer is no, it cannot yet distinguish, at least in our calculations, and we conjecture no. It cannot distinguish the invertibility at this moment yet. Okay, so I shall stop here and thank you for your attention.
Okay, thank you very much for a nice talk. Are there any questions or comments?
I have one question. For the higher right master move,
Yes.
can you say it is related to Rojman moves?
Yes, it is. Yes.
I
Rosman
mean,
moves
if
are-
we
yes. Yes, please.
sorry, if we consider movies of Rojman move, then we can get such a cycle, right? Is it right?
We can get such a what?
I mean, when we consider movie of Rojman moves,
Yes.
then, for example, there is a Rojman move with having 4 triple points. Then, for each part of the move, we can get a movie, and by connecting them, we can get such a how to say. In this example, we have 4 as 8 taper points, right? In this loop, we have 8 taper points, and 4 of them, we will get. If we separate it to 4, 4, then it is Rojman, one of Rojman. Can I understand like that?
So I suppose that the Rosman move version you used is for the movies, right?
Right.
Okay, for the movies, it turns out some Rosman moves coincide with the ones here, but I mean the movie moves have more singularities. Here
then
we have
yes.
less singularities. That's the difference.
Oh, I see.
Yes.
Understand.
So it is
Thank
included,
you.
yes, as a part of movie move, yes. But movie moves, since it is for the two embedded surface, they have more singularities, especially with the birth, death, or the how to say that I don't remember. Sorry, I don't
Saddle
remember.
point, yeah.
Yes, yes,
Saddle
saddle,
points,
saddle.
right.
For the saddles,
Yeah.
yes. So our higher random mass moves actually is just a strictly subset of that movie moves.
Understand. Thank you very much.
Yes.
Okay, any further questions or comments? How do you think, do we have a chance to get any combinatorial invariants of two-dimensional knots by themselves? So not just as something used for one-dimensional knots, but two-dimensional knots for themselves.
But two-dimensional knots for themselves is the thing is that since we have less singularities, so our method might not give an invariant for the two-dimensional knot, because it might not satisfy the extra singularities conditions, the extra moving moves. But another way might be possible, is that can we use the two knot invariants, come back to study these paths or loops in the space of long knots? I think this is possible. But I don't know whether I understand you correctly.
Okay. Okay, so thank you very much.
Thank you for the questions and the invitation.
Thank you very much.
Okay, thank you very much. Yes. Yeah, so that's all for today. Bye.
Okay.